Namaste, welcome back to the session of Turbomachines. In the previous session, we have gone through the derivation of energy transfer as well as a degree of reaction for radial flow turbomachines. We have seen the energy transfer equation in terms of outlet blade angle, which is nothing but beta 2, as well as the degree of reaction R in terms of outlet blade angle beta 2, because in case of power absorbing machines, outlet plays a very important role, because power has to be imparted to the fluid by the rotating element. In the sense, while entering into the machine, the fluid will be having no energy with it. It has to be entering at minimum velocity, and while exiting the machine has to impart the energy to it, and hence it will be at the higher energy or higher velocities. That is why outlet part plays a very important role in case of power absorbing turbo machines. In this session, we will be analyzing the radial flow turbo machines. One more analysis there with respect to the radial flow turbo machine. Here we have few basics regarding radial flow turbo machines. We are analyzing the things for radially outward flow turbo machines. We are not discussing the things for radially inward flow, but we are discussing the things for radially outward flow machines. I mean, our discussion will always be with respect to radially outward flow machines. Next thing is, all radial outward flow machines are centrifugal type, in the sense the energy to the fluid is imparted by the machine in the form of centrifugal act. In the sense, the rotating element of the machine is going to impart the energy to the fluid, thereby this rotary action of the blades of the machine is going to throw away the fluid outward from the center. That act is called as centrifugal act. In the sense, the centrifugal act of the machine is going to impart the energy to the fluid. So, all radially outward flow machines what we are going to discuss are of centrifugal type. And the last thing is no whirl at inlet. In the sense, there is no whirl, there is no tangential component of that of the absolute velocity at the inlet. In the sense, the component Vu1 is 0. That is what is the condition that we are imposing at the initial stage itself. So, now let us look on to the velocity triangles that we have. Here I have not written the general velocity triangles from where I have reduced these two. We have understood those things very enoughly in the previous sessions. So, directly I have written inlet as well as outlet velocity triangles. Let us look on to the inlet. One of the conditions says no inlet whirl. No inlet whirl in the sense Vu1 is equal to 0. Whirl at the inlet is 0. That is going to eliminate the tangential component at the inlet. So, Vu1 is equal to 0. Once Vu1 becomes 0, alpha 1 becomes 90 degree. So, and V1 is equal to Vf1. What is this condition? V1 is equal to Vf1 in the sense we are talking with respect to radial inlet. So, fluid is entering into the machine in such a way that from the circumference of the rotor it is rushing towards the machine center, I mean towards the rotor center. That is what is a radial inlet. So, V1 is equal to Vf1, V1 is equal to 0 and alpha 1 is equal to 90 degree. Then the relative velocity component Vr1 is making an angle of beta 1. Beta 1 is nothing but inlet blade angle with respect to the blade velocity at the inlet, and V1 becomes the flow velocity Vf1 since alpha 1 becomes a 90 degree. Next thing is, I mean, because of alpha 1 is equal to 90 degree, I am saying that V1 is Vf1, and then I can say that entry is radial. Next thing is outlet velocity triangle. Here one thing is for sure, for power absorbing machine U should be greater than Vu. In the sense, blade velocity should always be greater than tangential component of that of fluid's velocity. I mean, absolute velocity of fluids, one of the component Vu should always be less than blade velocity. blade is going to impart the energy to the fluid. In the sense, blade should be running at very high velocity, that is what is u. As soon as I look into the outlet velocity triangles, I need to check for one condition, the blade velocity u should be greater than Vu. Whatever I have written is satisfying the condition. Next thing is the distance between Vf and V, I mean distance between the absolute velocity and one of its component, which is nothing but flow velocity, should be the tangential velocity component Vu. That has been satisfied. Next thing is relative velocity and absolute velocity distance is nothing but blade velocity, that has been satisfied over here. So, whatever the triangle I have written is correct. Next, angle made by Vr with respect to the u is beta 2, angle made by absolute velocity with respect to u is alpha 2, and Vf2 is nothing but the flow velocity, which is always perpendicular in nature. Vf2 is equal to Vf1. So, that condition is V1 is equal to Vf1, which is equal to Vf2. This V1 is equal to Vf1 because alpha 1 is 90 degree. What do you mean by alpha 1 is equal to 90 degree? There is no whirl at the inlet. There is no whirl in the sense the entry itself becomes the radial entry, and Vu1 is equal to 0. Once the radial entry, I mean once the whirl at the inlet becomes 0, obviously Vu1 becomes 0. So, these are the things related to the velocity triangles. So, now I will be looking on to the analysis. We know energy transfer equation by the Euler's formula is given by E is equal to U2 Vu2 minus U1 Vu1. Here it is U2 Vu2 minus U1 Vu1 because it is a power absorbing turbo machine. Because of that, U2 Vu2 minus U1 Vu1. Next, in the next stage, E is equal to U2 Vu2 because Vu1 is equal to 0. That is what is the condition. No whirl at the inlet means Vu1 is equal to 0. Once Vu1 is equal to 0, this term will be equal to 0. That means this term will be vanished. So, I will be left out with U2 Vu2. We have discussed at the earlier stage that for incompressible fluids, what do you mean by incompressible fluid? Fluid's density cannot be changed over the machine. While fluid is moving through the machine, its density will not alter. If we are dealing with such a fluids, then energy transfer can be notated as energy per unit mass, which is given by G into H, where G is nothing but gravitational force, H is nothing but height with which the fluid has been lifted. So, energy transfer per unit mass will be equal to energy transfer which is occurring through the machine. This condition is for incompressible fluids. Then E can also be expressed as G into H, which is equal to U2 Vu2. I have called this equation as equation number 1. Now, I will go through velocity triangles because I need to search for the equation. On what parameters the energy transfer dependent on? U2 as well as Vu2. If I look on to the values of U2 and Vu2 in terms of blade angles, what this will become? That is what is the question that I need to answer now. So, now these two are the components with respect to suffix 2, in the sense with respect to outlet. That means I need to look on to outlet velocity triangle. Here is the outlet velocity triangle. Now, I will be looking for the value of Vu2. Vu2 is nothing but absolute velocity components horizontal, I mean absolute velocity is horizontal component. I am looking for Vu2. If I need Vu2, I will take outlet blade angle cot beta 2 is U2 minus Vu2, that is nothing but this distance. Cot beta 2 is adjacent divided by opposite. Adjacent is this, which is nothing but, look on to this distance. What is this distance now? U2 minus Vu2. So, U2 minus Vu2 divided by flow velocity at the outlet. U2 minus Vu2 divided by flow velocity at the outlet. Please solve the equation for Vu2. Vu2 becomes U2 minus Vf2 cot beta 2. What I am trying to do here is I am trying to express Vu2 in terms of outlet blade angle beta 2. Vu2 is equal to U2 minus Vf2 cot beta 2. I have called this as equation number 2, and I have got the value of one of the term present in the energy transfer equation, which is nothing but Vu2. This is what is with respect to this part. Next thing is I need to look for the Q. Q is nothing but the discharge of the fluid which is happening through the machine, the quantity of fluid which is flowing through the machine. So now I have written a sketch in order to look onto the Q that is flowing through the machine. So here is the blade of the turbo machine to us. This is the blade and this is the thickness of that blade, which is denoted by B. If I need discharge, which is nothing but area into velocity, we are very much aware of this equation. Area times of what is the velocity that I have to consider? I need to consider flow velocity, which is nothing but Vf. Flow velocity in the sense what? The velocity with which the fluid is moving through the machine. So that is what is Vf. Next thing is area through which the machine, fluid is flowing, is given by pi d1 b1. Pi is the term, d1 diameter of the rotor, b1 is the thickness of the blades. In the sense, this is the diameter into thickness. This diameter's thickness times of phi is the area through which the fluid is moving. So phi d1 b1 is the area and v is the velocity, Vf1. If it is at the inlet, the same thing happens at the outlet also. Inlet in the sense this thing, this portion. If you want the outlet, then I need to look onto this portion, which is nothing but phi d2 b2, flow velocity at the outlet Vf2. So the same equation will hold good the value of Q. Now we knew Vf1 is equal to Vf2 from the velocity triangles. Vf1 is equal to Vf2, flow velocity at inlet will be equal to flow velocity at outlet. Because of that, if I solve this equation for either Vf1 or Vf2, Vf becomes Q divided by pi d1 b1 or which is equal to Q divided by pi d2 b2. Now I have got the value of Vf, which is nothing but flow velocity. I will call this as the equation number 3. Now I will substitute 2 and 3 in 1. 2 is this, the value of Vu2, 3 is the value of flow velocity. I will substitute these two equations in equation number 1. Let us look onto the equation number 1, which is nothing but energy transfer Gh will be equal to U2 Vu2. Gh is equal to, I have kept U2 as it is and I have replaced Vu2 by the term what I have got by the equation number 2, Vu2 minus Vf2 cot beta 2. Inside this I have the term Vf2. I can look for Vf2, which is nothing but Q divided by pi d2 b2. Vf2 is Q divided by pi d2 b2 times of cot beta 2 and the rest of the terms are as it is. Now I will send the U2 inside and I will keep the H on the left hand side, so that I will get H is equal to U2 square divided by G minus Q divided by pi d2 b2 into G into this U2 has to go in U2 times of cot beta 2. So I have expressed H, head with which the fluid is getting lifted, by U2 outlet velocity, blades outlet velocity, as well as cot beta 2 outlet blade angle. So now H and Q are the main variables that we have expressed in this equation. So now we have analyzed the flow which is happening through the radial turbo machine, wherein if you look onto the various terms, all the terms are with respect to outlet. U2 blade velocity at the outlet, D2 diameter of the rotor at the outlet, B2 thickness of the blade at the outlet, so beta 2 which is nothing but blade angle at outlet. So now H and Q are the new variables that we have introduced in this equation, because those two terms have come because of this. The energy transfer has been splitted in terms of G and H, and Vf has been expressed in terms of Q. Now we have a standard equation. With respect to that equation, we need to look on how the flow, discharge Q as well as head with which the machine is operating are dependent on one another based on blade angles of the turbo machine. Okay, so now let us look on to the dependency of H on the Q for various blade outlet angles. Various blade outlet angle in the sense what? I will be looking on to beta 2, various blade angles, how this beta 2 is going to affect the head as well as discharge. So, now I will be concentrating on this beta 2. From the previous equation, what I have got is H is equal to U2 square by G minus Q divided by G phi D2 B2 U2 cot beta 2. Blade velocity at the outlet is U2, diameter at the outlet is D2, width at the outlet is B2, blade velocity at the outlet U2, beta 2, blade angles at the outlet. So, now all these terms are with respect to the outlet. Now, let us look for the variation. If blade angle at the outlet beta 2 is 90 degree, if it is a perpendicular 90 degree, then what will be the value of cot beta 2? If beta 2 becomes 90 degree, cot 90 is equal to 0. Now, let us look on to the term. I will keep beta 2 onto the one side. I will look on to this. This is the multiple of beta 2. This term is multiple of beta 2. Now, if cot beta 2 becomes 0, this cot beta 2 becomes 0, this multiple becomes 0. 0 into anything is 0. We will be left out with H is equal to U2 square divided by G, because this entire term will be vanished. In such situations, the beta 2 blade angle is 90 degree and the blades are termed as radial blades. I mean, at the outlet the blades are radial in nature. So, now this is the vein and I need to write the triangle for this situation. I know beta 2 is 90 degree. If beta 2 becomes 90 degree, VR2 will be overlapped on VF2, because beta 2 is 90 degree. That means what? Look onto this. This beta 2 has to be 90 degree, in the sense this has to be overlapped on this. Beta 2 has to be 90 degree in the sense this has to be overlapped on this. That means this distance, whatever U2 minus VU2 was there, that will be eliminated. I will be remained with U2, which is equal to VU2. So, this is U2. U2 beta 2 is 90 degree, wherein VR2 is VF2, and look on to the blades are radial. Those are nothing but 90 degree vanes. That means H is equal to U2 square by G. For radial outlet, the velocity triangle looks like this. Now, the second variation is when beta 2 is in between 0 to 90 degree. We have exactly look on to the value wherein the beta 2 is equal to 90 degree. Now, I will be looking on to the value when beta 2 is in between 0 and 90 degree. Cot beta 2 becomes positive, in the sense between 0 and 90, if you give any angle for beta 2, then cot beta 2 will hold a value of positive. That means what? If this is positive, if cot beta 2 is positive, then this entire term becomes positive. Am I right on that? So, this is positive, holding a value of positive. This will have certain value now, right? That means U2 square by G minus a certain value. U2 square by G minus certain value, I will have a positive value for H. Vanes are backward, in the sense what? Certain value minus this certain value is going to reduce the value of H, in the sense we will have a value for H as well as the Q. Now, in this situation, vanes are backward. Why we are calling it as a backward? What is the value of cot beta 2 now? It is not 90, it is less than 90. Look onto the outlet triangle, we will come to know. If we want radial, then beta 2 is overlapping on V of 2. If we want beta 2 less than 90, then this has to be inclined. This is what is the situation now. I have written the same situation in a reverse manner over here. Look onto the value of beta 2. Is it less than 90? Yes. That means the blades what we are going to get are backward vanes, wherein the value of beta 2 is less than 90 degree. I hope all other terms are very familiar to you. You need to concentrate on beta 2. Beta 2 is less than 90 degree. Because of that, the veins are backward veins over here. That is what I have written over here. Make sure if cot beta 2 is in between 0 and 90, cot beta 2 holds a positive value, and hence veins become the backward because of the vein angle beta 2 is less than 90 degree. We have left out with one more situation when beta 2 is in between 90 and 180. What do you mean by that? Beta 2 value should be in between 90 and 180. Cot beta 2 holds a negative value. For any value in between 90 and 180, cot beta 2 becomes negative. This cot beta 2 becomes negative. Negative in the sense what? Here already one negative is there. This multiple of q will have a, multiple of beta 2 will have a negative. This negative times of this negative becomes positive. That means the h is going to increase. Minus of minus will become positive. For this term, this will be an addition now. So that h becomes higher. That is what we have written over here. Once beta 2 is greater than 90 and less than 180, the veins becomes forward veins. That is what we have written over here. We need to just concentrate on beta 2. Look onto the beta 2. This is beta 2. This is VR. VR2. That is what we have written over here. This is beta 2. So now V2, beta 2 is greater than 90 degree and less than 180. Obviously, we can observe it from over there. Now look onto the veins direction. These veins become a forward vein. So now it is very clear. If cot beta 2, beta 2 becomes 90, veins are radial. If beta 2 is in between 0 and 90, veins are backward veins. If beta 2 becomes in between 90 and 180, then veins are forward. This plays a huge role in explaining the dependency of H and Q. How H depends on Q, that totally depends on outlet blade angle beta 2, because this Q totally dependent on multiple of this cot beta 2. This is the multiple of cot beta 2. If I remove the Q from that, cot beta 2 multiplication becomes this. Based on cot beta 2, I can say how Q and H are dependent because these two are fixed. So now Q and H can be explained with the help of the variation in cot beta 2. That is what I have written over there. This is called as HQ curves. HQ curves. So now we have three different situations for which I will be explaining HQ curve. Let us look onto the situation now. Very first situation is beta 2 is equal to 90 degree. If beta 2 becomes 90 degree, veins become radial. Am I right on that? Beta 2 is 90 degree, veins are radial, in the sense veins are perpendicular. Now substitute the values into this equation. If beta 2 is 90, cot beta 2 becomes 0. That means this entire term becomes 0. Cot beta 2 is 0, this entire terms becomes 0, and then look on to the value of H. H is not dependent on Q because Q multiple becomes 0. That means H is not dependent on Q. However, we increase the discharge, that is not going to affect the H in case of radial veins. That has been expressed in the form of curve. In the y-axis I have taken H, in the x-axis I have taken discharge Q. Now I am increasing the value of Q. I am increasing the value of Q, but this increment in the Q is not altering H because the H is constant if you increase the Q to any value. Why is that happening? Because beta 2 is 0. If I substitute 0 over here, this entire term becomes 0. Then there is no variation of H because of increment in Q. That is what happens for radial veins. H and Q are not at all dependent on each other. If we ask the HQ curve for the radial veins, then HQ, this is the horizontal line. I hope that is very clear. Next thing is if I look onto the value of beta 2 which exists in between 0 and 90. If beta 2 is in between 0 and 90, cot beta 2 becomes positive. If cot beta 2 is positive, this value will hold certain value. It is a positive value. This is a fixed thing minus certain value. Fixed thing minus certain value is going to decrease the value of H. If I increase the value of Q, look onto this, if I increase the value of Q, you need to play with this. If the value of Q is increased, then this multiple will become increased because this is having a positive value. If value of Q is increased, then certain fixed thing minus increment in the Q is going to decrease the H. That means if I go on increasing the value of Q, the head with which the turbo machine is operating will go down. That means H and Q are inversely proportional for beta 2 which is existing between 0 to 90 degree, or else I can call this as a radially backward vane turbo machines wherein H and Q are inversely proportional. That is what this is saying. I hope this concept is very clear now. And the last thing is, if beta 2 is in between 90 and 180, then cot beta 2 holds a negative value. That means if beta 2 is in between 90 and 80, this is a negative. This is a negative. Negative of this negative becomes positive. Now if I increase the value of Q, this is holding a positive now. If I increase the value of Q, that will increase the value of H. In the sense, Q and H are directly dependent. If I increase the value of Q, H is going to be increased. What kind of vanes we have at that situation? Which is nothing but the forward vanes wherein beta 2 is greater than 90 and less than 180. So these are the variations of H and Q for various blade angles. It is very clear now. If I increase the value of Q, H is not disturbed if the vanes are radial. If I increase the value of Q, the H is going to decrease if the blades are backward vanes. If I increase the value of Q, the H is going to increase if the vanes are forward vanes. So this is the conclusion that we can obtain by this discussion. Next thing is, we have one more term over here. If the Q discharge is 0, still we have certain amount of height here. If Q is 0, then we have certain amount of height here. What is this height? Even though discharge is 0, we have certain amount of height. Please look onto the equation. If I substitute Q is equal to 0, this entire term becomes 0. If this entire term becomes 0, still I will be left out with this. What is this? U2 square by G. So this distance is nothing but U2 square divided by G. This U2 square by G is called as shut-off head. That means the head at which the discharge is 0 is called as the shut-off head. Shut-off head is equal to H, which is equal to U2 square by G. This exists when the Q is 0. That means at this point the vanes are radial vanes. When the vanes are radial, still Q is 0, then also the value of H exists, which is called as the shut-off head H. So this is what regarding the analysis of radial flow turbo machines. We have looked on the dependency of discharge on the head, and we have discussed 3 different vanes such as radial, forward vanes as well as backward vanes. Along with that, we have discussed HQ curve. This curve is going to say us how H and Q are dependent for various vane angles. This is what is for the today's session. We will meet in the next session. Namaste.